Assalamualaikum warahmatullahi wabarakatuh. So today we're going to present Fourier applications. Our group members are Nurul Atika binti Hasman, Nurul Natasha binti Sahari, Nur Fatin Syahira binti Syahrudin, and Nur Ain Syahidah binti Jumiati. So let's proceed to the next slide.
So the first one, we would like to present about application of Fourier series in electrical engineering. Fourier transform is a special integral transformation. The Fourier transformation transforms the signal from the time domain to the frequency domain. We apply Fourier transform to circuit with non-sinusoidal excitation in exactly the same way we apply phasor techniques to circuit with sinusoidal excitation. So we use the formula V omega equal to I omega Z omega, where the V and I are the Fourier transform of the voltage and current, and Z omega are the impedance. The Fourier transform analysis has always been widely used in this field. For example, imaging processing. Fourier transforms tell you what is happening in the image in terms the frequencies of those sinusoids. For example, eliminating high frequencies blur the image. Eliminating low frequency give you a edge, and enhancing high frequency while keeping the low frequencies sharpens the image. So how it works? Basically, some bright spot occur in the middle of the image, which is correspond to the detail pattern. By removing the frequencies which we think correspond to the detail pattern, we can eliminate the detail from the image.
So for the calculation, 4 steps of using Fourier transform. The first one is convert all elements into omega domain, and second, convert the input signal to omega domain. Third, apply circuit analysis such as mesh, nodal, Thevenin's and Norton, or so on. Fourth, convert back the omega domain to T domain. So this is the calculation for the image process. For the image processing, let ST be a periodic signal having period T. We want to consider what happens to the signal spectrum as we let the period become longer and longer. We denote the spectrum for any assumed value of the period by CKT. We calculate the spectrum according to the familiar formula. So this is the formula where we have used a symmetric placement of the integration interval about the origin for subsequent derivational convenience. Let f be a fixed frequency equaling k over t. We vary the frequency index k proportionally as we increase the period. So and then making the corresponding Fourier series. So that is the formula. As the period increases, the spectral lines become closer together, becoming a continuum. Therefore, this is the formula where SF is the Fourier transform of ST and is defined for any signal for which the integral converges.
So I will proceed with the task 2, which is application of Fourier series in optics. What is Fourier optics? Fourier optics is the study of classical optics using Fourier transform, which the waveform being considered is regarded as made up of a combination or superposition of plane wave. Ray optics is a convenient tool to determine imaging characteristics such as the location of the image and the image magnification. A complete description of the imaging system, however, requires the wave properties of light and associated processes like diffraction to be included. It is these processes that determine the resolution of optical devices, the image contrast, and the effect of spatial filters. So next is optical spatial filtering. This filter consists of altering the image content by placing masks in the Fourier plane. These masks are to affect the amplitude and the phase of spectral components. So for the first one is low pass filtering. A simple kind of filter is the low pass filter frequently used in laser cavities to improve the beam quality. Such as like the diagram below. Secondly is the high pass filter edge enhancement. It consists of a dark spot in the center of the Fourier plane, and it is used to sharpen photograph. And thirdly, the image correction. This consider, for instance, the photograph of a video display. It is possible to eliminate the lines from the picture by inserting two knife edges in the frequency plane. And lastly, the image correlation. Uh, these more complicated filters can be made by photography, but one interesting application is the comparison of various objects with a reference one, for example, a set of alphanumeric characters.
Okay, next for the calculation of Fourier optics. And firstly, the optical spatial filtering calculation. In the infinite lens limit, it can be shown that the field distribution in the focal plane of the lens is given like in the formula. S is the object distance, F is the focal length of the lens, the R square equals to X square plus Y square is the coordinates in the focal plane. The FUV is the Fourier transform of the object function, and U equals to negative XF over lambda F, and V equals to negative YF over lambda F. The observable intensity pattern in the focal plane of the lens does not depend on the object position. Okay, secondly, the spatial Fourier transform calculation. The Fourier coordinates have units of inverse length and are called spatial frequencies. A plane wave of amplitude E0 impinges on the object. The field distribution immediately behind the object EXY equals to FXY. The object information is impressed onto the light wave. This optical process can produce the Fourier transform of EXY and the object function. Lastly, for diffraction, so this is the formula. A rectangular aperture is characterized by the transmittance function for A2 in between negative A2 in between and A2 and negative B2 in between B2, where the XY plane is the plane of the aperture. The intensity distribution in the far field diffraction pattern is in the formula above, where U, V are the spatial frequencies for the X and Y dimension. Strictly speaking, the far field diffraction pattern can only be observed at infinity by placing a lens after the diffracting aperture. The plane at infinity is imaged onto the focal plane of the lens. This explains why a lens can perform a Fourier transform. Okay, that's all for our presentation. Thank you.